welcome back or welcome. As you know, it's me again. I have not posted in a hot minute, probably since July, or if I even put that video out. Oh wait, no, I did it for world history. Anyways, here's an AP pre-calc video, and this is on topics. Since it's an AP class, it has specific topics, so this is going to be just kind of what I found helpful and notes that I found helpful in topics 1.1 to 1.4 slash just like the intro to AP pre-calc. So the first thing on the second day, my teacher introduced was functions and rates of change, otherwise and more simplistically known as slope. And he introduced an idea or just a tool that I never thought of before, and it's called the rate of change hand. So literally all you do to not establish but just be able to visualize and conceptualize rates of changes is you kind of match your hand to however the line is. Okay, so for example, if you have this as your line, or actually, yeah, let's use the fine line. So the rate of change is obviously very different in each of these spots, but to see if the rate of change is increasing or decreasing, you literally just put your hand to match how the line looks, essentially. And so if you want to figure out, I know this seems very duh, but for me, I kind of will get in my head and overthink about whether it's increasing or decreasing or whether it's positive or negative. And so you can kind of just use that, and I use that all the time to follow to see if functions are increasing or decreasing. And so you just follow your hand. So if your fingers are facing up, positive. If your hand's like this, it's 0. If your hand's going down, your finger's going down, it's negative. So I just never thought of it like that. This can also help you figuring out if rate of changes are increasing or decreasing. By that I mean if the rate of change is going less steep and less steep, or less steep and less steep, you know it's decreasing. I don't know. That just helped me out. So that's probably very obvious, but if you don't know, now you know. Another fact, I have kind of some rules. I'll probably put them up here. Increasing functions have to be increasing at every interval to be called an increasing function. So again, since this is an AP course, they're on the exam they're gonna want to trick you with a lot of terminology and stuff. But essentially, functions, in order to be deemed increasing or decreasing, they have to, at any point in any interval you look at, they have to be either increasing or decreasing. So quadratic functions are not increasing functions or decreasing functions. The only increasing functions, most functions, if they go up and down, they're not increasing because there's at least one interval where the rate of change is decreasing or 0. Secondly, all rate of change means is the average of 2 points. So you just do your slope formula and call it a day. To piggyback off of that, also functions that end and start on the same y value will have the same rate of change, or will have the same average rate of change. Let me show you what I mean. Okay, so you have your graph again, and you have starting point and ending point, right? To say this is x is, or y is 2. They're both on y, they both end here. So it does not matter what the hell happens in between here, because if the starting and ending point for the starting x point and the ending x point are in the same y value, okay, if the the starting point and ending point of a function are on the same y value, the rate of change will always be 0. No matter what happens in here, all that matters is the starting and ending point or behavior. Okay, I was just out of my hand taking notes. I'm gonna go into the actual book we have now. Okay, so the entirety of like 1.1 is just finding increasing intervals, which is a basic math skill. And if you're on here, I really hope you don't need that, because I've lost faith in myself if you don't know how to find intervals like that. Questions or just in general, that's something along the lines of, this is your function, you have points there, point there, point there, and point there. We'll call this A, B, C, and D. And you're asked which one has the greatest or least rate of change. The easiest way to do this is to draw tangent lines, which I will do in a different color. But tangent lines are just lines that skim and mirror, they mirror the linear function, how a linear function would look if it hit this exact point. What I mean by that, so you have like, see how that aligns with how the line looks right there, and then for B, and for C it would be here, and then for D it would be. So you can see, out of all of these, this is 0. This is the rate of change is 0. This has a negative rate of change. It's also going backward. Actually, no, it's just, no, that's a positive rate of change. But it's like almost going at like a 1-to-1 ratio. This one is going very negative. This is going very negative. This is going very positive. So A would be your correct answer there. Let's go on to tables. So one thing we've been working on is essentially being able to determine whether or not functions are linear, quadratic, or neither, just based off of tables, not the functions, not the graphs, just tables. So if you have a table that looks something like this, this is x, this is f of x, 1, 0, 2, 3, 4, 4. Okay, so this is sort of a simpler idea. I think I learned this in Math 8, maybe. But it's first differences and second differences, and subtracting f of x values to see if the rate of change is constant or just how it behaves, right? So first of all, you have to make sure your x values are increasing at a steady rate, so you have just a nice baseline. It's kind of like how you can't plot graphs with disproportionate x and y values. You can't say 1, 3, 9. You have to say actually specific constant values, like 1, 2, 3, 4, 5. You can't just skip around. It's the same idea here. You have to have the same rate of change. So even if this is 2, 4, 6, 8, it has to be increasing by the same amount. So it's just constant. So you don't have to deal with like all that, right? So once you do that, you have to figure out what the rate of change between the x values or the y values are. So you go there, and so this 1 minus 0 is 1, 4 minus 1 is 3, 9 minus 4 is 5. And so that is, oh, you can't see that. That is called your first difference. And so this is literally just seeing the rate of change between the x value or the y values. And if had these numbers all been the same, it would have been a linear function, because if the rate of change is constant the entire time, it's a diagonal line. But you attempt again to do a second difference, and if the second difference ends up being the same rate of change, it's a quadratic function. So you do a second, and look at that, 2 and 2. So it is a quadratic function. And so I will model another example of this, but it's just essentially seeing being able to determine what kind of graphs you're dealing with just by a set of numbers, just by a set of input and outputs. I'm actually not going to do another example, but if y'all need help with that, just comment down below and I'll make a separate video for that. So we have another kind of table, or it's like you have to basically see and predict, or not predict, how the functions play out just based off of inputs and outputs. So here's another table, got x and then f of x. And so we have, this one is determining whether functions are concave, up or down, right? So I'll show you how to do that. We have x1, 3, 5, 7, 9, and then we have -10, -6, -3, -1, 0. Okay, we're going to do the same first difference, second difference thing. Unless the first difference is linear, then we'll stop, okay? Check to make sure these are all increasing. These are all each increasing by 2 each time, so we are good there. So now we can work on find the rate of change difference between all of these. So we have -6 minus -10, which is 4, -3 minus -6, which is 3, -1 minus -3 is 2, and 0 minus -1 is 1. 4, 3, 2, 1. So how we determine how this will behave is, I think we kind of just assume it's a quadratic function unless you get neither, unless you don't get any logical answers. But basically, if the numbers are ascending from or descending from greatest to least, it's concave down. So you can just think like if the numbers are going down, it's concave down, because as x approaches infinity, y is decreasing. So on a graph, it would look like that. Something like that. So again, vice versa, if these numbers were going 1, 2, 3, 4, it'd be concave up. The next ideas are 4 graphs, and it is extremas / absolute minimums and maximums, right? So you have things called relative extrema and absolute extrema. So I'm going to draw this out a little bit. We'll say this is our function. So a relative extrema is just something that within its own area is the lowest possible thing. So the relative minimum would be a minimum point where both of its sides, every point on the side of it is increasing and is above it, okay? So this is the relative minimum because both of its sides are increasing, right? Same thing here, since there's nothing, this is where the function starts. Its only side is increasing, so this is also relative maximum or relative minimum. Same thing here, but for relative maximum, since it is the highest point of its area, it is relative maximum. So it's just kind of that. However, the global extreme or the global maximum is the overall highest point. So when you have, and you can only have absolute or global extrema in even functions. Well, unless the function's like this and it goes, and this will be the absolute minimum, but typically you'll just see it to where it's like these are the absolute maximums because the function, these are the absolute maximums because the function just won't go any higher than that. It's only going down. There's no absolute minimums because, again, it's going down. For here, there's no absolute maximums because it's always going up. Next, we'll go to, next are points of inflection. Shoot, I don't have a thing. Next are points of inflection, which is where functions go from concave up to concave down. So say you have that as your function. And so you have your graph from going from concave up, or I mean concave down, concave down to then concave up. So the point of inflection is just that little, like the mainly the relative point and like the estimate of where your function changes from being concave down to concave up. So it'd be somewhere over here. That's all that really means. Really everything you need to know out of my book my teacher provided me with, and my own written notes on topics 1.1 to 1.4 of AP Precalc. Bye-bye.